next talk. The next talk is given by Professor Yong Hu from Shanghai Jiao Tong University. So he will talk about the algebraic threefolds of general type with small volume. Now, please.
Thank you for the introduction. I would like to thank the organizers for the invitation, and I'm glad to give a talk here. Today, I will talk about my recent joint work with Tong Zhang. Okay, let me first introduce the geography of smooth minimal surface of general type. Throughout this talk, we always work over the complex number field. Now let S be a smooth minimal surface of general type. Then S has the following two basic invariants. C1 square, C1 is the first chain class of S, and C2S. These two are, it is known that they are integers. And it is well known that they characterize a minimal surface of general type up to a finite number of families. The first question in the geography of surface is the following one. For a pair of integers AB, here AB are both integers, when does there exist a minimal surface of general type S with C1 square is equal to A and C2S is equal to B? In fact, the chain invariants cannot be arbitrary. They have to satisfy the following equalities and inequalities. The first one is C1 square should be larger than 0 because S is minimal and it is of general type, and the C2S is larger than 0. The second one is Norton's formula. It says that C1 square plus C2 is equal to 12 times chi-OS, where chi-OS is a holomorphic Euler characteristic. So this means that C1 square plus C2 must be divided by 12. And the third one is not inequality. It says that C1 square is larger than or equal to 2 times PGS. Here PGS is the geometric genus of the surface, minus 4, which is larger than or equal to 2 times chi-OS minus 6. And this inequality is optimal. There are infinitely many examples satisfy the equality. The last one is called Mielka-Yau inequality. It says that C1 square is less than or equal to 9 times chi-OS, and it is also optimal. So now, first, I will give the following definition. Let S be a smooth minimal surface. S is said to be on the knot line if S is of general type and satisfies C1 square is equal to 2 times PGS minus 4. Because this is one will see that this is just not equality. Here is the not inequality. This is just the equality case. Horikawa classified the smooth minimal surface on the knot line. The theorem is the following. Let S be a smooth minimal surface on the knot line. Then the first statement is that the canonical map of S induces a double cover over a rational surface Y. He proved that the canonical linear system of S is space-bound free. So it is the canonical map is a morphism, and it induces a double cover over a rational surface Y. And the second statement is that the minimal resolution of Y is either P2 or a Hertzsprung surface. The third statement is that S is simply connected, which means that the topological fundamental group of S is trivial. Now, I would like to introduce the geography of high-dimensional varieties of general type. Now, let V be a d-dimensional smooth projective variety, and let omega V be the canonical line bundle, which is the determinant bundle of the holomorphic cotangent bundle. because omega v is a line bundle, then there is a associating, or there is a corresponding divisor, which is called the canonical divisor, and denoted by kV. The canonical volume of V is defined as the following one. This is the limit sup H0 V nkV over nd over d factorial. And it is easy to see that the canonical volume of V mirrors the growth of the plurigenus. When the canonical volume of V is larger than 0, V is said to be of general type. If V is of general type by BCHM, we know that we can replace V by its minimal model X, provided that the property we are studying is birationally invariant. In particular, we have the canonical volume of V is equal to the canonical volume of the minimal model X, and it is equal to KXD. Here, minimal model means that X has at worst Q factorial terminal singularities, and the canonical divisor of X is the Neff Q Cartier divisor. So this implies that the canonical volume of V is a rational number. Here is a theorem proved by Meng Chen and Zhijiang in 2017. They proved that let D be a positive integer, then there exists positive constants AD and BD, such that the inequality of not a type, the canonical volume of V is larger than or equal to AD PGV minus BD holds for any smooth projective default V of general type. If D is equal to 1, then we know that V is just a smooth algebraic curve. Then the canonical volume of V is just 2 times PGV minus 2. This holds for any smooth projective curve of general type. If D is equal to 2, we know that the knot inequality told us that we can take A2 is equal to 2 and B2 is equal to 4. And this is optimal. So how about the case when the dimension is larger than or equal to 3? Here one sees that this is just 2pg minus 2 times 1. And this is the canonical volume is larger than or equal to 2pg v minus 2 times the dimension 2. So one may guess that in high dimension is the knot inequality is just the canonical volume is larger than or equal to 2pgv minus 2d. But this is not true. Horikawa constructed the following examples. The theorem is for every integer e is larger than or equal to 3. There is a smooth projective threefold V of general type, such that the canonical divisor KV is ample. The geometric genus of V is just 3 times E minus 2, and the canonical volume is equal to 4 over 3 times the geometric genus PGV minus 10 over 3. And so this is just a rational number 4 over 3. This starts from dimension when dimension is larger than or equal to 3. This may not be an integer. And note that in Kobayashi's examples, we always have the geometric genus is equal to 1 modulo 3 for threefold V of general type constructed by Kobayashi. Here is 3e minus 2. So this is just 3 times e minus 1 plus 1. For the following theorem proved by Yongkai Chen and Meng Chen in 2015. It says that the inequality canonical volume is larger than or equal to 4 over 3 times the geometric genus minus 10 over 3 holds for all Gorenstein minimal threefolds of general type. So by Kobayashi's examples, we know that this is optimal. And recently, a theorem proved by Yongkai Chen, Meng Chen, and Chen Jiang in 2020. They proved that let V be a smooth projective threefold of general type, and either the geometric genus is less than or equal to 4, or the geometric genus is larger than or equal to 11. Then the following optimal inequality of node type holds. The canonical volume is larger than or equal to 4 over 3 times geometric genus minus 10 over 3. Here, in this theorem, they need the assumption that the minimum model, the canonical divisor KV of the minimum model is a Cartier divisor. But here, they drop this assumption. And this inequality is optimal also due by Kobayashi's example. So the optimal result naturally leads to the following questions. This question is also raised by Yongkai Chen, Meng Chen, and Chen Jiang. The first part of this question A is that, is there a classification for minimal threefolds X of general type satisfying the canonical volume kx cubed is equal to 4 over 3 times pgx minus 10 over 3? The second question is that, is there any non-Gorenstein minimal threefold X of general type satisfying the canonical volume kx cubed is equal to 4 over 3 times geometric genus minus 10 over 3? The answer to the first part of question A can be viewed as an analog of Horikawa's work in dimension 3. Regarding the second part, Kobayashi first constructed a series of examples of minimal threefolds X of general type satisfying the equality. Later, Yifan Chen and I generalized Kobayashi's method to obtain more examples. Recently, Meng Chen, Chen Jiang, and Bingru Li, they found 2 new examples via different method. And all these examples are Gorenstein. So all the minimal models, all the minimal models has Cartier canonical divisor. The question B is also raised by Yongkai Chen, Meng Chen, and Chen Jiang. Is there a second knot inequality in dimension 3? Namely, is there a real number B is less than 10 over 3, such that if the canonical volume kx cubed is larger than 4 over 3 times pgx minus 10 over 3 for minimal threefold X of general type, then the canonical volume is larger than or equal to 4 over 3 times pgx minus b. Here b is a constant. Let me recall some facts about the surface. For a minimal surface S of general type, note that for minimal surface of general type, S is smooth, so the canonical divisor Ks is Cartier. So it is easy to see that Ks square is always an integer. Thus, the second knot inequality is naturally that the canonical volume is larger than or equal to 2 pg minus 3, because this is an integer, and when the canonical volume is larger than 2 pg minus 4, it is at least 2 pg minus 3, and it is actually optimal. And Horikawa constructed a lot of examples satisfying this equality. However, when the dimension is larger than or equal to 3, the Cartier indices of minimal threefolds X of general type are unbounded. So it is not clear whether minus 10/3 is an accumulation point of the following set. This set is just the kx cubed minus 4/3 pgx. Here x is just the minimal threefold of general type. We know that this is larger than or equal to minus 10/3 when the geometric genus is larger than or equal to 11. But we don't know whether this number is the accumulation point of this set. So this is the main obstruction to the existence of the second knot inequality in dimension 3, not to mention the optimal one. Any questions so far? We say, now I give the definition. We say a minimal threefold X of general type with geometric genus is larger than or equal to 11 is on the knot line if kx cubed is equal to 4/3 times pgx minus 10/3. This is just the three-dimensional analog of the knot equality. So we say that this is on the knot line. Our first main theorem gives an initial description of threefolds on the knot line. This is a joint work with Tong Zhang. Theorem 1 is that let X be a minimal threefold of general type with geometric genus is larger than or equal to 11 and on the knot line, which means that the canonical volume of X is equal to 4/3 times pgx minus 10/3. Then the following statements hold. The first one is the geometric genus is equal to 1 modulo 3, and the X is Gorenstein, which means that the canonical divisor is Cartier. The second statement is that H1 XOX, the first irregularity of X is 0, and the second irregularity of OX is also 0. And the canonical image, here the canonical image means that the image of the canonical map of X, because the geometric genus of X is larger than or equal to 11. So the canonical map is non-trivial. The canonical image sigma is in this projective space of X is a non-degenerate surface of degree pgx minus 2. Note that the dimension of this projective space is just the pgx minus 1. So the non-degenerate surface has a degree at least pgx minus 2. So this is just the minimal degree. And the sigma, and this surface is smooth when the geometric genus is larger than or equal to 23. The last statement is that every smooth model of X is simply connected. So the topological fundamental group of X is trivial. After we finished our paper, Professor Yongkai Chen informed us that under the assumption that the canonical image sigma is the surface, he has got a proof of theorem 1 using a different method. So he also, when the canonical image sigma is the surface, he also proved that the minimum model is Gorenstein. But the method is very different. So now let us compare theorem 1 with the corresponding results in dimension 2. For surface, now let S be a minimal surface of general type on the knot line. Bomberry proved that the irregularity of S is just 0. And Horikawa proved that the canonical image, which is the image of the canonical map of S, sigma in pgs minus 1 of S is a non-degenerate surface of degree pgs minus 2. So this one is a surface, and it is also This is a non-degenerate surface, and it is also of minimal degree. And sigma is smooth when the geometric genus is larger than or equal to 7. And Horikawa also proved that S is simply connected. So our theorem 1, the statement 2 to 4 shows that similar results hold in dimension 3. So the H1 and H2 is 0. The canonical image is also of minimal degree, is a surface of minimal degree. And it is smooth when the geometric genus is a little larger. And X is, every smooth model is simply connected. This phenomenon is new because for surface on the knot line, there is no restriction on the geometric genus, but for threefolds, the geometric genus should be 1 modulo 3. And notice that there exists a minimal threefold X on the knot line with geometric genus which is equal to 19, whose canonical image is not smooth. Thus, the lower bound geometric genus is larger than or equal to 23 in our theorem 1.3 is almost optimal. This example is constructed by Meng Chen, Chen Jiang, and Bingru Li. Notice that their constructed geometric genus is 19. So the last case is 19 plus 3, which is 22. And after 22 is larger than or equal to 23. So the only missing case is when the geometric genus is equal to 2012. We don't know whether there is these examples with geometric genus is equal to 22 and the canonical image is not smooth and the threefold is on the knot line. So theorem 1 answers the second part of question A in the negative when geometric genus is larger than or equal to 11. Let me recall the second part. The second part is asks, is there any non-Gorenstein minimal threefold X of general type satisfying this equality? This is not an equality. So our result shows that all threefolds on the knot line is Gorenstein if geometric genus is larger than or equal to 11. So this gives a negative answer to the second part. To answer the first part, let me first recall the geometry of 1-2 surface. We say that a smooth projective surface S is a 1-2 surface if the canonical volume of S is equal to 1 and the geometric genus is equal to 2. Now let S be a smooth minimal 1-2 surface. Then it is well known that the canonical divisor or canonical linear system of S has a unique base point P. If we blow up this point P, denoted by S prime, then the movable part of sigma up star Ks is base point free, and it is composed with a rational pencil of curves of genus 2. So from S prime, there is a fibration to P1, whose general fiber is a smooth curve of genus 2. Now, if we have a family of this minimal 1-2 surface, let F from X to B be a minimal fibration over a smooth projective curve B such that the general fiber F of this F is a minimal 1-2 surface. So on each general fiber, there is a canonical base point. There is a unique base point of the canonical linear system of the fiber. So the fibration F has a canonical section gamma, whose intersection gamma with F, where F is any general fiber. It's just the base point of Kf. you can just consider the relative canonical map. This gamma is just the horizontal base locus of this vibration. This gamma is just the horizontal base locus of the relative canonical map of this vibration. So now I would like to give the answer to the first part of question A. Let X be a minimal threefold of general type with geometric genus larger than or equal to 11 and on the knot line. By our theorem 1, we may write note that geometric genus is equal to 1 modulo 3. So we can write it as 3 times m minus 2 for an integer m, which is greater than or equal to 5. Now, a key observation is that there exists a minimal threefold x1, which is birational to x, such that x1 admits a fibration from x1 to p1 with general fiber a 1-2 surface. So from the above discussion, we know that F has a natural section, which is the horizontal base locus of the relative canonical map of x1 over p1. And this section is just the canonical section introduced here. Now let x1 to p1 is the relatively minimal. This is the minimal fibration. So we can consider the relatively canonical model. Now let x not be the relative canonical model of x1 over p1 with the induced fibration from f0 from x0 to p1. Then the canonical section gamma descends to a section gamma naught of f0. We say that x0 is the relative canonical model associated to x, and the gamma naught is the canonical section of f0. In general, this x0 may not be the canonical model of x, so it may not be unique, but it is birational to x. We classify the geometric structure of this x0. Our theorem 2 says that let x be a minimal threefold of general type with geometric genus is equal to 3 times m minus 2, which is larger than or equal to 11, and on the knot line. Let x not be the relative canonical model associated to x with a fibration f0 from x0 to p1. And the general fiber of this fibration is just a canonical 1-2 surface. Now, recall that this fibration has a canonical section gamma naught. So we can let x naught prime be the blow-up of x naught along the canonical section gamma naught of f0. Then the induced fibration from x0 prime to p1 is factorized as the following. This is the fibration. First, it affects to this p1 bundle Fe and Y. This is a fibration, and this is a finite morphism with the following properties. The Hertzsprung surface Fe is isomorphic to the relative. This is isomorphic to the relative canonical map of f0 prime. And Y is the p1 bundle over the Hertzsprung surface. Here, S, notice that Fe is larger than or equal to 0. S is the section with S square is equal to minus E. And L is the ruling on Fe. So Fe is the p1 bundle over p1, and Y is the p1 bundle over the Hertzsprung surface. The third statement is that x0 prime to Y here rho is a flat double cover with a branch locus B, which is equal to B1 plus B2. And B1 is the relative hyperplane section of Y. and B2 is linearly equivalent to this guy. And the B1 intersect with B2 is empty. Moreover, if the geometric genus of X is larger than or equal to 23, then X0 is exactly the canonical model of X. So when the geometric genus of X is larger than or equal to 23, X0 is just the canonical model, so it is unique. Recall that every minimal surface of general type on the knot line is birationally a double cover of a P1 bundle over P1. This is proved by Furukawa. So our theorem 2 asserts that birationally every minimal threefold of general type on the knot line has a similar structure. So this is just a double cover over P1 tower. This is a P1 bundle, and this is a P1 bundle over P1. Here, I would like to add a remark. A closely related question raised by Yongkai Chen and Qingrui Lai asks whether a minimal n-fold X of general type, here n is larger than or equal to 3, with canonical volume is equal to n plus 1 over n times PGX minus n squared plus 1 over n, is under some extra assumptions birationally a double cover of a tower of P1 bundles. Note that when n is 3, this is just 4 over 3, this is just 10 over 3. In fact, they constructed, for any n is larger than or equal to 3, they constructed examples satisfying this equality. Theorem 2, so our theorem 2 gives a general affirmative answer to this question for n, which for n is equal to 3, when the geometric genus of X is larger than or equal to 11, and we don't need the extra assumptions. So the main result of theorem 2 is just the following. So now we suppose X0 is the relative canonical model associated to the minimal threefold X on the knot line. Then we have the following commutative picture. This is just the fibration from X0 to P1. And we blow up of X0 along the canonical section gamma naught. We get X0 prime. This is a fibration. So conversely, you can think X0 comes from here. You start from P1, and you can get a P1 bundle FE. And over FE, you can get a P1 bundle Y and take a double cover. And we can get X0 prime and just do a divisorial contraction. We get X0. So X0 is just a divisorial contraction of a double cover over 2 tower P1 bundle over P1. So the structure of X0 is just this. This gives an answer to the first part of question A. We also proved 2 new knot type inequalities. This is our theorem 3. Let X be a minimal threefold of general type with geometric genus larger than or equal to 11. Suppose that the canonical volume Kx cubed is larger than 4 over 3 PGX minus 10 over 3. Then we have the optimal inequality. Kx cubed is larger than or equal to 4 over 3 PGX minus 19 over 6. And if the equality holds, then the geometric genus is equal to 2 modulo 3. Moreover, X has only one non-Gorenstein terminal singularity, and it is of this type. This is just the C3 to C3. The group action is like Z1, Z2, Z3 to minus Z1, minus Z2, minus Z3. So this is just the quotient singularity. Suppose that if Kx cubed is larger than 4 over 3 PGX minus 19 19/6. Then we have the optimal inequality. Kx cubed is larger than or equal to 4/3 pgx minus 3. This inequality is also optimal. We constructed many examples satisfying this equality. If the equality holds, then the geometric genus is equal to 0 modulo 3. So this is divided by 3. Moreover, when the equality holds, one of the following two cases occurs. The first one is that X has two non-Gorenstein terminal singularities, and they are of the same type, of this type. The second is the following: X has only one non-Gorenstein terminal singularity, and it is of type CA1 quotient is isolated CA1 and quotient by cyclic group of order 2. Moreover, if X attains the equality in either, if X is satisfying this equality or this equality, then the statement 2 to 3 or 2 to 4 in theorem 1 also hold for X. Here is our theorem 1. So when the other two equalities hold, we also have H1 XOX and H is equal to H2 XOX is equal to 0. And the canonical image of the is also a non-degenerate surface of minimal degree. And every smooth model of X is simply connected. Here, the assumption the geometric genus is larger than or equal to 11 is also optimal, because there exists a minimal threefold of general type with geometric genus which is equal to 10, and kx cubed is equal to 4/3 pgx minus 33/10, which is less than 4/3 pgx minus 19/6. And you can see that this is larger than 4/3 pgx minus 10/3. So when the geometric genus is less than or equal to 10, this inequality may not hold. And by theorem 1 and theorem 3, for any VP in this number satisfying, here P is an integer which is larger than or equal to 11. V is a positive integer satisfying V minus 4/3 P, which is not in this, which is not this one of these three numbers. The first is minus 10/3. The second is minus 19/6. The last one is minus 3. And V minus 4/3 P is less than minus 3. There does not exist a smooth projective threefold V of general type such that the canonical volume is equal to V and the geometric genus is equal to P. The picture is just like this one. So we have, here is the geometric genus PG, and this is the canonical volume. So this one is the not inequality. We know that and this is our second not equality. This is our third not equality. So for points here, one cannot, for any V P here, there is one cannot find x such that the canonical volume of x is equal to v and pg x is equal to p. So here there is no threefolds, and here there is also no threefolds. Now I would like to give a sketch of proof. It is clear that to prove the above theorem, here is the proof of theorem 1 and theorem 3, which is just related to the inequality. Note that both inequalities are very close to 4/3 PG minus 10/3. So we may assume that the canonical volume is related to 4/3 PGX is very small. So we may assume that X is a minimal threefold of general type with geometric genus is larger than or equal to 11, and kx cubed is less than 4/3 pgx minus 8/3. This inequality is stronger than these three inequalities because 8/3 is less than 3. So we may assume that this inequality holds. We only need to consider this case. Now let phi kx from x to this projective space be the canonical map of x, which is just the rational map induced by the canonical linear system. And we denote by sigma the canonical image. We first show that sigma is just a smooth, or it is a surface, which means that the dimension of sigma is 2. Here x is a threefold, so sigma can be a threefold or surface or curve. By a result of Kobayashi, we know that the dimension of sigma is less than or equal to 2. When sigma is a threefold, the canonical volume is larger than or equal. Kobayashi proved that the canonical volume is larger than or equal to 2 times PG minus 6, which is stronger than this inequality. So we have dimension sigma is less than or equal to 2. The key result we prove here is that sigma cannot be a curve. When sigma is a curve, we proved that kx cubed is larger than or equal to 4/3 pgx minus 8/3, which is a contradiction because we assumed kx cubed is less than or equal to 4/3 pgx minus 8/3. So there is a gap 2/3, which is equal to 10/3 minus 8/3 between threefolds on the knot line and the threefolds whose canonical image is a curve. So we proved that the sigma is a surface. So when sigma is a surface, we know that the degree of sigma, because sigma is non-degenerate, so the degree of sigma is at least pgx minus 2. We proved that under this assumption, the degree sigma can only be pgx minus 2. So sigma is a non-degenerate surface of minimal degree. And we assumed that geometric genus is larger than or equal to 11. So sigma can be a Hertzbrucher surface or just a cone over a rational curve, over a smooth rational curve, which is of minimal degree. So in both cases, we can get the fibration. So the second step is that we using the geometry of the surface sigma, we prove that up to a birational modification, X admits a fibration from X to P1 with general fiber a minimal 1-2 surface. Here, the key point is that the fibration is on the minimal model X, not just the relative minimal model. And with the help of this fibration F, we prove that the irregularity of X and the second irregularity of X is equal to 0. Moreover, we prove the following two key estimates. The first one is that kx cubed is larger than or equal to pgx plus 1/2 and round up of this guy, 2 pgx minus 1/3 minus 3. So here you can see that when pgx minus 1 is not divided by 3, this will be larger. The second one is that p2x, which is the second plurigenus, is less than or equal to round down of 2 kx cubed plus the round down of 2 kx cubed minus 5 pgx minus 1/3 plus 7. This may looks a little strange, but it is very important in our proof. And based on the above two estimates and a careful analysis by Miles Reed's Riemann-Roch formula, his formula is just p2x is equal to 1/2 kx cubed plus 3 chi omega x plus L2x. We know that chi omega x is just pgx plus qx minus h2x minus 1. So now we know that qx and h2ox is 0. So we know chi omega x is just the pgx minus 1. And we know kx cubed. And now this gives the upper bound of P2. So we can get the upper bound of L2x. Here L2x is the correction term, which is just the contribution of the terminal singularities. And when this guy is 0, L2x is 0, is equivalent to that canonical divisor of x is a Cartier divisor. So we prove that the two inequalities are the desired optimal Noether type inequalities. Furthermore, when x attains the equality in any of these three equalities, we know very precise information of this L2x when x attains the first Noether equality. We know that L2x is just 0, and these two, we also know L2x. So we are able to fully describe the non-Gorenstein singularities on x. Thus, theorem 1 and theorem 3 are proved. So this relies, our proof relies heavily on Reed's Riemann-Roch formula. So how to prove theorem 2? Now we suppose that theorem 2 is just the classification of threefolds satisfying the first Noether equality on the Noether line. Now we suppose that kx cubed is equal to 4/3 pgx minus 10/3, and the geometric genus of x is larger than or equal to 11. By the argument here, we may assume that by the assumption here, we know that x has after taking some birational modification, we may assume that X admits a fibration from X to P1 with general fiber a 1-2 surface. Here is the minimal fibration, so we can let X not be the relative canonical model of X over P1. Here we have a canonical section gamma, and the canonical section gamma descends to X0. So our F0 from X0 to P1 has a canonical section. We first show that the base locus of this canonical linear system Kx0 is just this canonical section. And we prove that the canonical section gamma naught lies in the smooth locus of X0. So it does not intersect with the singular locus of X0. And we can blow up of X0 along gamma naught. X0 prime also has the canonical singularities. And this is a smooth curve. So the exceptional divisor is a P1 bundle over the canonical section gamma naught. And we denote by E naught the exceptional divisor. We show that the rational map phi from X0 prime to P F lower star omega X is the flat morphism. In fact, priorly, we only know that this is a rational map. We prove that this is a morphism, and in fact, it is a flat morphism with all fibers are integral curves of genus 2, and all fibers are in fact Gorenstein curves. And we set E to be phi lower star OX naught prime 2E naught. We prove that E is a locally free sheaf of rank 2. So this is just a vector bundle of rank 2. And 2E not restrict to every fiber is just the canonical divisor of the curve. So we can consider the relative canonical map of this fibration. This is just the induced from X0 prime to PE. This is our Y. Sorry. This is just our Y here. So we get the PE. And we prove that this is a flat double cover. And then, because it is a flat double cover, and we can compute the branch locus of this row. And we prove that here we only know that it is a locally free sheaf of rank 2. We prove that this locally free sheaf splits into the direct sum of 2 line bundles. And we obtain the explicit description of the corresponding line bundles, which is just this one. E is just this one. The direct sum of a trivial bundle and this line bundle. And when the geometric genus of X is larger than or equal to 23, we prove that the Kx0 is ample. So here, because X0 is the relative canonical model of X over P1, so Kx0 is just the F0 relative ample. We prove that when the geometric genus is larger than or equal to 23, Kx0 is ample. So X0, because X0 has adverse canonical singularities, so X0 is just the canonical model of X. And when X0 is the canonical model of X, we can prove that the images, the canonical image sigma is smooth. So we finish the proof. I think I stop here. Thank you very much for your attention.
Okay, thank you. Any question?
So in your statement of your main theorem, so you say something about the simply connectedness. That so you know the simply connected only for its resolution, or how about for its minimal models?
We proved that the smooth model of X is simply connected because X has terminal singularities. Then by result of Takayama, X is simply connected.
Okay, so X itself is also simply connected, right?
Yeah, yes.
Thank you.
So can you explain the main idea of proving that for any threefold, which is canonical fiber of 1-2 surfaces, then the slope is -8/3. So what's the main idea?
Sorry.
So you how to prove this?
This is a combination of the techniques developed by Yongkai Chen, Meng Chen, and Chen Jiang's work, the technique, and the results in the previous joint work in my previous joint work with Tong Zhang for irregular threefolds of genotype.
Okay.
In this case, you have a vibration from X to P1, and you can consider the Kx plus 2F.
Yes.
And you can also use the weak pseudo effectivity of 3 pi upstar Kx minus something F. And we can give some more give some.
Okay. Do you also use so the technical part? So in our proof is that we in that place we have to use weak positivity. So for some divisors, so you just choose a more delicate divisor, right? And then you prove this, right?
Yeah.
Okay. So so the -8/3, this is optimal, right?
Yes. Oh, no. We don't know. We don't know whether it is optimal. Or not. We just know that this is stronger than our than these three equalities.
Okay.
We don't have examples.
Okay, more questions?
So in the case where that PG is divided by 3, so you say that it's possible to have two quotient singularities, or it also might possible to have a CA quotient singularity, right?
Yeah.
But so that the baskets are the same, right?
Yes, the baskets are the same.
Okay. Yeah. Thank you.
Okay, if no more question, so let's thank Yonghu, and so also thanks very much to the organizers for the 2 talks this afternoon. Especially to
Thank you
Professor
too, Chairman, for the
Hai Hong.
sharing work.
Okay, so thank you very much.
Thank
Yeah.
you.
Thank you. See you again. Nice. In 2 weeks, yeah. We'll meet again in 2 weeks.
Okay.
Okay. Yeah, bye-bye.